All right, so this section, section 3.3, is just going to give us a quick summary of the studies that we've talked about. The challenges of establishing causation. So we're going to, in this section, take a look at when can we establish causation and when can we use our scope of inference for a larger population based on the experiment that we did. We're going to define the scope of inference. So basically, who can we apply the results of the experiment to, and can we establish cause and effect? And the last thing that we're going to quickly take a look at is describe the data ethics in designing studies. So basically, what kind of studies can we actually perform on people? There are lots of experiments that, we'd like to test, but we can't necessarily do because it would be unethical. Okay, so the first thing is how can we make conclusions beyond the data that we've collected? So the U.S. Census Bureau carries out a monthly current population survey of 60,000 households. Their goal is to use this data from these randomly selected households to estimate the percent of unemployed in the population. So as you read your various situations or various experimental designs, there's some key things that you're going to want to look for. Okay, so the key thing that you're going to look for, the takeaway from this section, is that the data was randomly selected, okay, from a certain amount of households. Well, what can we do with that information? All right, so number one, it was key that the individuals were randomly chosen. So what does this allow us to do? This allows us to help avoid bias and provides trustworthy results about the population. All right. When you have random selection, it does not necessarily establish cause and effect. It just allows you to apply the results to a larger population. Since they were randomly selected, you know that you have less variability in your sample and that your sample is a good representation of the population. All right, let's take a look at a second example. All right, this deals with sleep deprivation. All right, I used to tell my athletes this, so I was kind of excited when I came across this study. Scientists performed an experiment that randomly assigned 21 volunteer subjects to one of two treatments: sleep deprivation for one night or unrestricted sleep. The experimenters hope to show that sleep deprivation causes a decreased performance in 2 days later. So I always tell everybody that the night before the big event is always the important night's sleep, because of this study right here, that sleep deprivation doesn't cause a decreased performance the next day, but 2 days later. All right, so how is this one different than our U.S. Census Bureau question? Well, in our Census Bureau question, they were randomly selected. In this question, they were randomly assigned to sleep deprivation or unrestricted sleep. So the key here is that the subjects were randomly assigned to the treatment. Since they were randomly assigned to the treatment, we can make inference about cause and effect. So did sleep deprivation for one night cause a decrease in performance 2 days later? We can make that inference based on the fact that they were randomly assigned to the treatment. But who can we make that inference about? We can only make it about those in the study, since everybody in the study were volunteers. All right, so we can't make it about a larger population because the volunteers might not be a good representation of the entire population. All right, so in the next couple slides, we're just going to be taking a look. Can we actually make inferences from the above studies, or what type of studies can we make inferences about? We're going to be able to answer the question on what type of inferences can be made. All right, so can we make an inference to the entire population? Or can we establish cause and effect? Randomization is going to help us to decide which type of inference, if any, is appropriate. Okay, so randomization based on randomly selecting and then randomly assigning the subjects to the various treatments. Okay, so what exactly does random selection do? We can make inference about the larger population, not just the sample that we selected. So when we have random selection of our participants, the reason that we can make inference about the larger population is if they were randomly selected, they're a good representation of the entire population, not just everybody that volunteered for the study. All right, what does random assignment do? Random assignment allows us to make inference about cause and effect. Since we randomly assigned the treatment to one group or the other, okay, it reduces variability within the groups, and it's not all people of, everybody that eats really healthy diets is getting one treatment versus people that don't get healthy diets get another treatment, okay, when they're mixed between the two treatments, and we can establish cause and effect. All right, so just make sure you understand the difference between random selection. Random selection allows inference about the population. Random assignment allows us to make inference about cause and effect. Please check the wording of the question carefully to see if there's random selection and random assignment. So what I would start doing, and this is going to be important as you're going through later sections, I would start underlining, highlighting keywords in the questions that you're given. All right, so what exactly type of inference can we make from a particular study? So the answer depends on the design of the study. So remember, that's going to be random assignment and random selection or a simple random sample, okay? Not sure why I wrote SAS. Okay, so well-designed experiments, if we have a well-designed experiment, they randomly assign the individuals to the treatment groups. However, most experiments don't always select experimental units at random from a larger population. All right, an example would be a lot of universities do a lot of studies, a lot of hospitals do a lot of studies, and they ask for volunteers for a study. You can often look up, it used to be in the newspaper, you can probably look it up online, you can get paid $300 for the weekend to go and have a skin rubbed on your, or a cream rubbed on your skin, and then come back 2 days later and see if you have a reaction. You're going to be a volunteer in that situation, which means that we can't necessarily make inference about a larger population. So this often limits experiments to inferences about cause and effect. Thus, the cause and effect will only apply to those in the experiment. So we might be able to establish cause and effect, but we can only do it to those in the experiment. So you have to read the wording of the question very carefully. Now, observational studies obviously don't randomly assign individuals to groups because whatever we're looking at has already happened, we're just observing it. So this rules out inference about cause and effect. All right, observational studies often use random sampling, which can make inferences about the population from our studies, but we can't necessarily establish cause and effect. All right, so take a look at the table below. We're just to see if you can make inferences about the population and cause and effect. So for example, the top says, were the individuals randomly assigned to groups? And then the rows, or were they randomly selected? So if they were randomly assigned to groups and they were randomly selected, you can make inference about the population and cause and effect. If they were not randomly assigned to groups and they were randomly selected, okay, we can make an inference about the population because it's a good representation of the population, but we cannot establish cause and effect because the treatment was not randomly assigned. Okay. Now, if they were not randomly assigned to groups, okay, we cannot make an inference about the population. If they were randomly selected, if they were not randomly selected, then we cannot make an inference about the population. But if they were randomly assigned to groups, then yes, we can establish cause and effect. And then if neither happened, obviously, that's not a very good experiment. So we cannot make an inference about the population, and we cannot make inference about cause and effect. All right, so there are challenges of establishing causation. All right, a well-designed experiment tells us that changes in the explanatory variable cause changes in the response variable. All right, so if you have sleep deprivation, do you actually have you don't perform as well on a task 2 days later. So lack of realism can limit our ability to apply the conclusions of an experiment to settings of greater interest. All right, because sometimes it isn't practical or ethical to do an experiment. So let's take a look at these questions. Does texting while driving increase the risk of having an accident? Well, you can't have people text and drive and see if they have an accident. The only thing you can do is look at accidents that have actually occurred and seen if people were texting and driving. Okay, so that's more of an observational study. Or the other thing you could do is a simulation. So you could have a simulation of people texting while they're driving. Do they crash the car, not crash the car? But it's not going to happen where you can assign people to text or not text while driving. So does going to church regularly help people live longer? Okay, well, you can take a look at people that actually do go to church, look at their, the length of their lives versus people that do not, but it's not really an experiment that you can perform because you can't force people to go to church. Okay, and then how about, does smoking cause lung cancer? Well, you can't tell one group of people to smoke their whole lives and one group of people not to smoke their whole lives. That's not very ethical. Can't do an experiment on that. But we could take a look at people that have smoked versus people that haven't smoked. So we can do all of these in an observational setting, but we can't do an experiment about it. However, it is sometimes possible to build a strong case for causation in the absence of experiments by looking at data from observational studies. Okay, so sometimes we can use observational studies to help establish cause and effect, but there's going to be some specific guidelines to do that. All right, so when we can't do an experiment, we use the following criteria for establishing causation. Number one, the association is strong. So oftentimes, if I look at all of the car accidents and I notice that in 75% of the car accidents, people are texting and driving. The association is consistent. So consistently across the board, when I look at car accidents and were people texting or on their phone, it's consistent across the entire United States, okay? It's not 1 month where there weren't any car accidents and 1 month there were a whole bunch, so it's consistent. So larger values of the explanatory variable are associated with stronger responses. So more texting and driving causes more accidents. So the alleged cause precedes the effect in time. So what this is basically saying is, for example, smoking. So if we look at people that have smoked and then look 10 years later to see if they have lung cancer, okay, we're looking over time to see what has happened. And the alleged cause is plausible. So does this actually make sense? Does it actually make sense if you're texting while you're driving that you're going to cause a car accident? All right, so take a look at this example. I'd like you to take a minute and describe how each of these criteria apply to the observational studies of the relationship between smoking and lung cancer. Okay, so when they say that smoking increases lung cancer, obviously they haven't forced people to smoke to see whether or not they have an increased rate of lung cancer. They use an observational study. However, the observational study had to follow these guidelines before you could, officially publish information about the study. Okay, so let's see how you did. Number one, the association between smoking and lung cancer is very strong. So a lot of people that have lung cancer have smoked in the past. The association is consistent. So consistent says that many studies of different kinds of people in many countries link smoking to lung cancer. So it's not just one study, studies all over the world. This reduces the chance that some other variable specific to one group or one study explains the association. So this is basically like reducing confounding. So was it smoking that caused lung cancer, or was it the air quality? Well, if it's done in China where the air quality is bad and smoking still increases your risk of lung cancer, but it's also done in the United States and in Alaska, which is also part of the United States, and South America and New Zealand and Russia, and they all come up with the same results, we can't necessarily say that it's just the air quality. It could be the fact that smoking does increase lung cancer. People who smoke more cigarettes per day or smoke over a longer period get lung cancer more often. Okay, so increased response in the explanatory variable causes an increased response in the response variable. People who stop smoking often reduce their risk. So lung cancer develops after years of smoking. The number of men dying of lung cancer rose as smoking became more common with a lag of about 30 years. So that's the overtime thing. So lung cancer kills more men than any other forms of cancer. Experiments with animals, now some of you may say this is unethical, shows that tar from cigarettes do cause cancer. The evidence for causation is overwhelming, but it's not as strong as the evidence that would have been provided by a well-designed experiment. So we do have really strong evidence based on our observations, but obviously we can't do an experiment on this situation. Okay, so what are some data ethics? So data ethics are complex issues of data arise when we collect data from people. So there's some basic standards of data ethics that must be obeyed by all studies that gather data from human subjects, both observational studies and experiments. So it wouldn't be ethical to force people to smoke. It wouldn't be ethical to force people to text while they're driving. It wouldn't be ethical to force someone to go to church. So what are some basic data ethics? So all planned studies must be reviewed in advance by an institutional review board. So if you want to have a study that's going to hold up, you can't just create some sort of study in your basement and say, oh, I established cause and effect. There are people out there that they look at protecting the safety and well-being of your subjects. So maybe doing an experiment in your basement is not going to provide a safe environment. So all individuals who are subjects must give their informed consent before the data is collected. So they have to understand that they're in the study and that they're participating. They don't know whether or not they're getting the treatment or the placebo, okay, but they have to actually agree to be in the study. And all data must be kept confidential. So only statistical summaries for groups of subjects may be made public. So you can write a summary, but you cannot write specific names of people as you're writing your summary. So in this section, we just learned about the inference about the population. So remember that in order to make an inference about the population, we have to randomly select, okay, and we need to randomly assign treatments if we want to allow for cause and effect. So the lack of realism can prevent us from generalizing its results. Like I said, you can't force people to smoke, drive, or go to church. In the absence of an experiment, good evidence of causation requires a strong association that appears consistently in many studies, is a clear explanation for the link, and a careful examination of possible lurking variables. Was it the air quality in China or the smoking that caused lung cancer? So studies involving humans must be screened in advance by an institutional review board. All participants must give their informed consent, and any information must be kept confidential.